Greetings. Heat exchangers are very popular thermodynamic applications in engineering. They present a good example of the first law where heat transfer results in a change in enthalpy, and also a good example of the second law where heat transfer causes entropy generation. Still, there is an ambiguous point between two bodies with different temperatures. First, what is entropy generation due to heat transfer? And what is entropy transfer due to heat transfer? The present problem tries to clarify these points. This problem states that we have a heat exchanger. So there is a heat exchanger which, let's draw it this way. There is a heat exchanger. This is our heat exchanger. And it is an adiabatic heat exchanger. So it is an adiabatic heat exchanger. Which means that Q equals 0, or Q dot equals 0. Now, there are two sides to this heat exchanger. One side is water. Let's draw it on this side. One side is water, where a stream of water enters the heat exchanger and leaves. So let's put it this way. The inlet temperature, T in, equals 260 degrees C, and T out, the exit temperature, T out, is 150 degrees C. So we have the knowledge that both inlet and exit temperatures for the water are known. We also know its mass flow rate. We know that the mass flow rate for water is 9100 kilograms per hour, 9100 kilograms per hour, and its Cp, we are told, is 4.18 kilojoules per kilograms Kelvin. Since we have water, it's compressed liquid, Cv or Cp, and generally speaking, C, specific heat are very close. It's always the same. We get the same value for them. Now, this is water. On the other side, there is oil. On the other side, there is oil. And what we know about oil is T in, inlet temperature, is 30 degrees C. We don't know T out. We don't know T out, but we know its mass flow rate, m dot O, equals 27,300 kilograms per hour. And we also know a property of oil, which is its Cp, and that is said to be 3.55 kilojoules per kilograms Kelvin. Now, please note that what I did here was to draw both inlets from the top out. So the flow here goes from top to bottom, and the flow here goes from top to bottom, which means these two streams are parallel flow. We could have drawn it counterflow, and once I have solved this problem at the end, I will try to explain the difference and show what a parallel flow or a counterflow heat exchanger would entail. But at this moment, there's no difference for us, so let's just go ahead with the solution. So this is the problem. What does the problem want from us? It wants us to simplify the conservation equations. First, find out the exit temperature for oil. Also, it asks us to find the entropy generation. In fact, you would calculate and see all of these things just now. Now, as for mass conservation, to write mass conservation, we need to decide which our control volumes are. And there are many choices of control volume. In fact, I would do 4 different choices in this solution, but you could take less or more. One control volume is this one, which is just around water. This one is one control volume, which is just for water. The next one is this one, which is just for oil. The third control volume is the whole heat exchanger. And there is a fourth control volume, which I shall come to it later on. Look, this control volume, it is water. It is warmer, so we know that it loses heat. There is no work because there is no moving boundary. There is mass in and there is mass out, and it is steady. This control volume receives heat, and there is a mass in, mass out. There's no work since there's no moving boundary, and therefore it is steady flow. Now, the third control volume is the large one, which there is no work for it. There is no heat transfer associated with it. And there are mass coming in and going out. There are 2 streams of mass coming in and going out. So we have 3 different control volumes, and we shall write our equations for all these 3. So for the water heat exchanger, water control volume, which is this one, it is water flow. And what is our mass conservation? It is 0 since it's steady, equals m dot I minus m dot E. You see, I have these equations, and what we have here, I'm writing this equation. Since it is a steady flow, this term vanishes, and then the inlet and exit mass the sum of inlet and exit mass would be 0. It would be the same for this one. Since it's steady, the left-hand side is 0, and for the second law of thermodynamics, the left-hand side would be 0 as well. For all this problem, work is 0. For any equation that we write for this problem, work is 0. So we have 2 distinct 0 terms. One is work, and the other are the left-hand sides of all 3 equations. So let's return and see how we can write the um, mass conservation law for um, oil site. For oil site, for oil flow, 0 equals m dot I minus m dot E. And the conclusion we make from these two equations is that m dot I equals m dot E, okay, and m dot for water is 9100 kilograms per hour. So this is what we conclude for this stream. You see, it might look very clear that whatever enters goes out. But look, we are using thermodynamic terms, thermodynamic language. And the thermodynamic language tells us to write this equation, okay, and conclude from it that whatever goes in exactly also leaves the control volume. And the mass flow rate was 9100 milliliter and left the control volume as 9100 as well. So this is, remember, this is the thermodynamics language. We could repeat the same practice for the oil side and then m dot O, which is the same for inlet and outlet, would be m dot O equals 27,300 kilograms per hour. There would be little point in writing the mass conservation equation for the whole control volume. Why? Because we have two streams that don't mix. So even if we write it as two entry and two exit, it will be just the sum of these two terms. Okay, it will be 0 equals m dot I minus m dot E for water and plus m dot I minus m dot E for oil. But since they don't interact, they don't mix. There, nothing more will be given us. Each mass is acting independently. So there's little point in writing it. Still, we can write it. It will be just the sum of these two terms for the heat exchanger. For the heat exchanger, we could write 0 equals m dot I minus m dot E for water plus m dot I minus m dot E for oil. And that's all there is to it. We can't add these terms together because we can't add water and oil together. There is no point in it. It would be beneficial. This is not a practice for all terms because we would see that it would be beneficial if we do this for energy conservation because they would interact and exchange energy, but they don't exchange mass. So this is what we get for the mass conservation equation. Our next step is to write down the energy conservation for the three control volumes of our problem. And the energy conservation equation, energy conservation equation that we need to simple is this equation, the second equation. And as I mentioned, um, since the problem is steady, this left-hand side is 0. Since there is no work, this term work is 0. And now for the steam and oil side, there are heat transfers. They would be equal, but with opposite signs. And there are mass that enter and mass that leaves. There are no changes in velocity, or we just ignore any changes in velocity. They would be very small. And there are no changes in elevation, or at least they are small enough to be ignored. So the energy equation would look like this. For the water flow, once again, for the water flow, what we have is that 0, since it's steady, the left-hand side is 0, equals m dot water hi minus m dot water he. I have ignored elevation and changes in velocity. Now plus the heat transfer from water. This is the heat transfer we have from water to the oil. And this is the heat transfer we mean. You see, this heat transfer is leaving our control volume, and so its value should end up to be negative. But this one, since it's entering the oil control volume, should end up to be positive. We don't force it, it should happen. But just if we write our equations correctly, then it should happen that this ends up negative and this ends up positive. The values should be the same, but the signs should be different. As for oil flow, 0 equals m dot oil times hi. Of course, these hi's are different. This is for water, this is for oil. Minus m dot o he plus q dot oil. This is since I'm writing these equations, one for water and for oil, then I just won't put subscript here for in every case. And for heat exchanger, for heat exchanger, and for heat exchanger, 0 equals m dot water times hi minus he, which is all for water, plus m dot oil times hi minus he, and that is for oil. There are no heat transfers since the total heat exchanger is adiabatic. So we have 3 equations, and we may now try to see which ones we can solve. Of course, what happens is that for the water flow, we have inlet and exit. For oil flow, we have inlet, we don't have exit, and we don't have heat transfer. And this is also another term which, with only one unknown, in this equation there is only one unknown, which is the exit from the oil. So let's see how we handle these equations. Well, we now may write the first equation for water flow as q dot equals, let's say, q dot water, which is heat transferred from water, equals m dot water times he minus hi, which equals m dot water Cp times TE minus TI. And now we may insert values into this equation, which equals m dot, which is 9100 kilograms per hour divided by 3600 to turn it into kilograms per second times 4.18, which is its specific heat, and times two temperatures, which are 150, is exit temperature, plus 273.15, because all calculations should be in kelvins, although most measurement instruments measure temperature in degrees C, but calculations should be in kelvins. I know that 273.15 would cancel out from this equation, but still, it's a good practice to keep it here, just to remember that all calculations are in kelvins. 150 minus 260 plus 273.15, and the outcome Q dot would be minus 1162.3 kilowatts. Well, once we have calculated the heat transfer water, we may move to the third equation, and in the third equation, we know this term, because this term equals Q dot water, and now we could calculate this term. So what we do is that for the heat exchanger, we are writing this equation, which is 0 equals, now replace this one with Q dot water, which would be minus Q dot water. The minus sign comes from the fact that here we have HI minus HE, and so we have just moved the Q dot water to the other side, plus M dot O times HI minus HE. This value is minus, this comes to the other side, which becomes plus, but it keeps this minus sign, and then for it would be minus 1162.3 equals M dot O times CP and times TI minus TE, which would equal 27,300 divided by 3,600 to turn it to kilograms per second times 3.55, which is the specific heat, times, and now turn all temperatures to kelvins, 30 plus 273.15 minus TE plus 273.15. And the outcome for TE, the exit temperature, is 73.2 degrees C, which is the exit temperature for the oil site. I could write it here, that now we know that the exit temperature for the oil side is 73.2 degrees C. This is the value we have now calculated, and we know it. Now, it's good practice to just replace everything in here and calculate Q dot O, which would entail oil flow and here we have 0 equals minus 1162.3 plus Q dot O, and the outcome would be Q dot O equals 1162.3 kilowatts. So what we have done, we have used our three equations. We have used our three equations very systematically and managed to calculate that this Q dot W, which is the heat lost from water, this is 1162. This is minus 1162.3, and this one is plus 1162.3. They have two different signs, but the same heat transfer. One is loss and the other is gain. Here, the heat transfer is 0. Look, we could have calculated these terms just by our general knowledge, but I tried to do it very systematically from the equations so that we would learn how to calculate from the thermodynamic language. And it's very important that we follow that language in thermodynamics. We have now covered the mass conservation law and the first law of thermodynamics for this problem. In the next video, we shall go for the second law of thermodynamics, the entropy generation, and the irreversibilities. Cheers.